You saw in section 4.1 that the derivative can help you figure out what your original function graph looks like just by knowing whether the derivative is positive or negative. That will tell you whether your function is increasing or decreasing. In this section, we're going to take it a step further, and the second derivative is going to tell us about the shape of the graph. But first, let's go back and review. You are going to have a local maximum where your derivative, your first derivative, changes from a positive to a negative at some x value. So let's just say I've got a graph in here, and we'll call this x location, we'll call that C. So at some x value, okay, you'll have a local max if your derivative changes from a positive to negative. The first example of this is if the derivative actually equals 0 at that location. So this would be an example. At that exact location, you've got a derivative of 0. So again, your derivative changing from positive to negative. Now, the only difference is if your derivative does not exist there, you may have a graph that has a cusp or a corner, but either way, you still have to have a positive slope to a negative slope. Okay, that would also indicate a local maximum. Now go ahead and do the local minimum and check your answers. Sometimes I wonder if I give you enough time, but hopefully you're ready to go. Okay, so those are local minimums. The first picture showing where the derivative equals 0, and the second picture showing the derivative not existing. Remember, these are critical points. Critical points are where derivatives equal 0 or fail to exist at interiors. Just a reminder, if your derivative does not change signs, then you have no local extrema. So an example of where the derivative equals 0 but the derivative does not change signs would be something like maybe a plateau at that location. Or the derivative not existing, maybe just the reverse of that with a vertical tangent. Okay. But either way, in each case, here we have f prime greater than 0 followed by f prime greater than 0. So no change of sign. Same thing here, f prime greater than 0, f prime greater than 0. So you have to have a change of your derivative sign in order to have a max or a min. Okay? We talked about endpoints a little bit in section 4.1, but this is just a reminder. You are going to have a maximum at your left endpoint. Okay, let's say you've got an endpoint of an interval at x equals a. As long as the derivative is less than 0, meaning you have a negative slope, you're going to have a maximum at your endpoint. If your derivative is greater than 0, meaning the slope is positive after that endpoint, you're going to have a minimum. So go ahead and do the endpoints for the right endpoints and show what the derivative would, or show what the function would have to look like and how your derivative would match up with that. Okay, so again, for the graph of f of x, this is supposed to be filled in. At an endpoint, on the right endpoint of the interval, as long as your derivative is less than 0, that's not quite right. These are flip-flopped. Your derivative, pardon me about that. This is your derivative would have to be greater than 0. Sorry about that typo. And here your derivative would have to be less than 0. Okay, so positive slope leading up to that right endpoint, negative slope for a minimum. Okay, so again, I apologize for the typo, but hopefully it makes sense. It seems pretty intuitive. Don't overthink things too much in this section. Okay, as I said at the beginning of this video notes, we're going to move on to seeing what the second derivative can tell us. And there's something called concavity. And concavity really tells you about the shape of the graph. A function is said to be concave up on an interval if y prime is increasing. Now, if y prime is increasing, its derivative would be greater than 0. Okay, so here's an example of something that is concave up. Okay, if you think about the tangent lines, so this would be f of x. Okay, if you think about the tangent lines, they are all positive slope, but the slope at each location is becoming more positive, so the derivative itself is increasing in value. Okay, so that's an example of concave up. Concave down says that y prime would be decreasing, meaning its derivative, y double prime, is less than 0. An example of that is if you had, again, this would be f of x. If you had a function whose tangent lines were always negative, but the slopes are becoming more negative, so y prime would be decreasing. Okay. Essentially, I like to kind of remind people a shape that has something that looks like a smile would be concave up. Something that has a shape that looks like a frown is concave down, which makes sense. If you're in a good mood, your mood is up, you'd be smiling. And if you're down, then you'd be frowning. So again, it's just the second derivative talks about the shape of the curve and essentially how our derivative values, whether they're increasing or decreasing. Okay, so example 1 is asking you to determine the concavity. This is very similar to what we did when we did finding maxes and mins and increasing, decreasing, only we're just talking about the second derivative values. So the first thing is the function itself is always continuous. It's a cube function. There's no even roots, there's no logarithms, and there's no denominators that could present domain errors. So the first thing we're going to do is take the first derivative, and that will give us 6x squared. And then if you take the second derivative, you'll get 12x. The second derivative talks about concavity. Okay? So if you want to know about concave up or concave down, you just need to determine the sign of the second derivative. So much like we did with the first derivative, we're going to set the second derivative equal to 0 to figure out where the second derivative changes sign. Okay, so here's my x number line. This is not a critical point. Critical points come from the first derivative equaling 0 or not existing. So this is just a possible change of concavity, but it is not a critical point. So we're going to go ahead and label f double prime of x because I want information about the second derivative. If you test a point to the left of 0 into the second derivative, you're going to get a negative value out. And if you test a point, so the second derivative was 0 here, and if you test a point to the right of 0 into the second derivative, you're getting out a positive. Okay, what does that tell you about your function itself? That tells you that it's concave down and then it's concave up. Okay, and if you want to think about a picture of what that would look like, it would look something like this, and then it would look something like this. Okay, so if you want to justify this, you would say the function f of x is concave up from 0 to infinity because f double prime of x is greater than 0. And you would say f of x is concave down from negative infinity to 0 because f double prime of x is less than 0. So there's your justification. That is what the AP graders would look at, just this little portion right here. Okay? Okay, a point of inflection. So here we go, more vocabulary. A point of inflection is any point on a graph where the graph has a tangent line And the second derivative changes signs is called a point of inflection. So on our previous example, at x equals 0, we had a point of inflection. The second derivative changed signs, and at x equals 0, there would be a tangent line. The function is continuous there. So that's just a vocab word. We're going to deal more with that when we practice problems. Let's go ahead and revisit section 3.4, where we talk about velocity and acceleration and all that wonderful stuff. So I'm going to have you do this example on your own to see what you remember, and then we'll check your answer. So go ahead and press pause now. Okay, so there's a lot of work here. Let's talk through it and see how you did. The first thing we're going to look at is the velocity. Take the derivative of the position and you should get 9t squared minus 18t plus 9. This is a continuous function, so we are only going to check for where the derivative equals 0. Pull out the 9 and you'll have this, which factors. Set it equal to 0 to find out where the velocity equals 0, and you're going to get a t value of 1. Now I made my number line, but it was specified up here in the original problem that t has to be greater than or equal to 0. So when I did my number line, I kind of darkened from 0 on to indicate that that's the domain. At t equals 1, we have a velocity of 0. And if you have a velocity of 0, that indicates that your particle is stopped. In between 0 and 1, if you test numbers into the velocity, you're going to get a positive value out. And if you do it again to the right of 1, you will also get positive values out. So that indicates that your particle is moving to the right in both areas. Okay, so that's all the information we can glean off of the velocity. Now, if you take it a step further and you talk about the acceleration, take the derivative of the velocity, and it's easier to do it from the unfactored form up here. So you'll get 18t minus 18, set it equal to 0, and you're going to get a t value of 1. It won't always happen this way that they're the same value. For this one, it happened that way. So again, set up your acceleration number line. T starts at 0 and goes to the right. We have a value of 1 here where the acceleration is 0. And if you test values in each region, you'll get a negative, then a positive. So what does that mean? Well, your velocity talks about, the sign of the velocity will indicate which direction your particle is moving. Together, the velocity and the acceleration can tell you the speed and whether it's increasing or decreasing. Okay, so I've summarized the top number line in this first little sentence here. The particle is moving to the right, 0 to 1, and we're using a bracket on 0 because that's an endpoint. 0 to 1 union with 1 to infinity. You cannot just say 0 to infinity because at t equals 1, the velocity is 0, so it's not moving at all. Okay, so you have to separate this into two little regions here. And your justification is that the velocity is greater than 0. Now, if you move this up a little bit, and you'll see I've written that the particle is speeding up. So we're increasing speed from 1 to infinity. And you look here, the velocity is positive, as is the acceleration. Remember, when the velocity and acceleration have the same sign, that indicates that the particle is speeding up. The particle would be slowing down or decreasing speed anytime the velocity and acceleration have opposing signs. Okay? But let's go back and remember that this is just talking about a graph, the position function, and then its two derivatives. So the first derivative, this is s prime of t, right? That's what the velocity is. It's the first derivative. And that indicates increasing or decreasing for your position. So the particle would technically be starting and moving to the right, stopping, and then moving to the right. Okay, or the position would be increasing. Now, we just learned from this section that your second derivative, that's s double prime, the sign tells you about the curvature. So the function will be concave down and then concave up. So if you put these two pieces of information together, you're getting a position function. I'm going to draw it in red over here to the side. You're getting a position function that would start, it would be increasing but concave down, and then it flattens out, and then it's increasing but concave up. So this would be at the location t equals 1. Okay, so now we're really getting to pull all this information together. And this is just the general sketch. So go back and revisit anything that you need to listen to or watch again. But this is really tying section 3.4, 4.1, and 4.3 all together. Okay, so first and second derivatives can really tell you a lot about the function. And there's one more little blurb we're going to talk about here. Local extrema. There's something called the second derivative test. And if you know your first derivative is 0, and if your second derivative, there's a little typo there. Let's try that again. If your second derivative is negative, pardon me, then that indicates a local maximum. So let me block that out. A couple little typos on this one. I apologize for that. Okay, so if you have your first derivative equaling 0 and your second derivative is negative, then f will have a local maximum. Well, think about it. If you've got a function that is concave down, meaning it's frowning, and at a location, the first derivative is 0, meaning it's got a horizontal tangent, that could only be a maximum. Okay? And then for your first derivative equaling 0, but f double prime being positive, man, typos all over the place. I really apologize. Then you're actually going to have a local minimum. Okay? So please fix those in your notes. If you've got a function and that is a concave up function for that one, it's smiling the whole time. If you've got a location where your first derivative equals 0, that would be right there. And if your second derivative is positive, then f has a local minimum, and that would be this place right here. Okay, so it's just one more way in order for you to determine if something is a max or a min. And that sums up this lesson. Okay, talk to you later. Bye.